Namaste. Today we will discuss about a strong viscous interaction, right? So in the previous classes we had a discussion on in a flat plate how there is a formation of strong interaction and the weak interaction, right? Based on the boundary layer, and then we had a discussion on outrage of the boundary layer, and then the boundary layer thickness, displacement thickness, right? So now we will go a little deeper into the strong viscous interaction. I acknowledge John D. Anderson's hypersonic and high temperature gas dynamics, right? So this is what the discussion we had in the previous classes, right? So we have a strong interaction when there is a flow over a flat plate, when there is a V infinity is very much greater. It is supposed to be a hypersonic flow. There is a formation of boundary layer, and we can say that there is a strong interaction which corresponds to d del star by dx is large. And here when it is moderate, we can call that as a weak interaction, right? So we know that, and then we move to the characteristics of the strong interaction. And in the strong interaction, we understand that d del star by dx is large, effective body having rapidly growing thickness, then the inviscid streamlines are displaced upwards, shock wave is developed, and then the inviscid regions are strongly affected. Then there is a feedback from the outer inviscid flow to the boundary layer. When the interactions are strong, these are all the characteristics we experience. Now let us start with the discussion further. Say in the strong interaction, the d del star by dx is larger, right? That's the primary discussion we have made when there is a formation of boundary layer. Again, we already know that the k is a parameter which you can discuss about m1 theta or m infinity tau, and in this case we consider this is d del star by dx. We had a discussion on how d del star by dx is equated to d tau and all those things. Anyway, let us continue further. Here we can consider that in the strong interaction, we can have the information that k square is very much greater than 1. And hence, the term which we have already used, say, for example, the pressure, right? Say the pressure PE by P infinity. That is what we had before in the last class. Let us write PE by P infinity. That is equal to 1 plus gamma into gamma plus 1 by 4 k square plus gamma k square into root of gamma plus 1 by 4 square plus 1 by k square. So this is what the equation we have arrived for PE by P infinity when we were discussing about the role of chi bar in the hypersonic interaction. Now let us say that by considering the assumption of k square is very much greater than 1, we can further write, say, PE by Px, which can be equated to gamma into gamma plus 1 by 2, because here you have 1 by 4 and here 1 by 4, then k square. So this 1 by k square, when k square is very much greater than unity, then we take it, we neglect this particular term. Now this we can equate, right? So we can equate this to the gamma into gamma plus 1 by 2 into, we know that k square, k is equal to m infinity, k is equal to m infinity into d del star by dx. Hence, we can write here m infinity square into d del star by dx square, right? So we have a equation, pressure equation here, and we already know that we have a boundary layer equation, right? So what is the boundary layer equation we had already? Say here the boundary layer equation del star, that is proportional to x by root of Reynolds number and then m infinity square into root of c by pe by p infinity. So we know the equation for del star and we know the equation for pe by px. Now, to couple the boundary layer with the outer inviscid flow, let us substitute this P by Px into the del star. So let us note that to couple the boundary layer equation with outer inviscid layer, right? Outer inviscid layer or outer inviscid flow, we can say, right? Say outer inviscid flow, then we can write the del star, which is proportional to x by root of Reynolds number into m infinity square into root c by p infinity, right? So that we can write here as 1 by m infinity into d del star by dx. Now we have coupled the boundary layer equation with the outer inviscid flow, right? So let us write this equation in the other form. Say del star into d del star, which is proportional to root of c by Reynolds number into m infinity x into dx. We can reduce this equation, right? Anyway, we already know the Reynolds number is equal to rho infinity v infinity x by mu infinity. And hence this equation, hence we can write this equation del star into d del star, that is proportional to root of c mu infinity by rho infinity v infinity into m infinity x. Already that x here and x power 1 by 2, hence we can write here as x by 2 into dx, right? Now let us integrate the above equation. We can integrate the equation and we can get the del star right here, del star and the d del star. So let us write this equation as del star square that is proportional to root of C into mu infinity by rho infinity V infinity and M infinity and x bar 3 by 2. Right? X bar 3 by 2. Right? So now let us reduce this equation further, right? So we want to calculate del star. So I recommend you to go further with the del star. Right? Okay. So let us calculate that del star is proportional to C mu infinity, mu infinity by rho infinity V infinity, the whole power 1 by 4 into M infinity for 1 by 2, and we can write x for 3 by 4. So the important physical result is that the conventional boundary layer results that the del star which grows parabolically, and that is like uh, in terms of x bar 1 by 2, right? So we can say that in the strong interaction region, so let us write in the strong interaction region, we can write del star that is proportional to x power 3 by 4, right? So, right. So let us again differentiate this equation, and we can get d del star by dx that is proportional to C mu infinity by rho infinity V infinity the whole power 1 by 4, then M infinity or 1 by 2 into x power uh, 1 by 2, right? 1 by 4 minus 1 by 4. So when you integrate x power 3 by 4, then so here in the strong interaction region, the same strong interaction region, d del star by dx is proportional to x power minus 1 by 4. So if we combine the equation PE by P infinity and d del star by dx, then it leads to PE by P infinity, that is PE by P infinity, which is proportional to x power minus 1 by 2. So this is what our results is. Right? So we can say that for a strong interaction, the variation of induced pressure is an inverse square root variation, right? So let us write finally, say the d del star by dx that is proportional to c mu infinity by rho infinity v infinity rho infinity v infinity over 1 by 4 into m infinity power 1 by 2 into x power minus 1 by 4. That is what our equation, previous equation. D del star by dx. Yeah. Okay. So we can write again d del star by dx, which is proportional to c by, I write this as a Reynolds number, and hence you have a 1 by 4, right? So we can write c by Reynolds number power 1 by 4, then m infinity power 1 by 2, because this x gets cancelled, right? And hence we can write k square, that is equal to m infinity square into d del star by dx square which is in turn proportional to m infinity cube by root of Reynolds number into root c. So this is in turn chi bar, right? Or chi bar. This is chi bar, and now we know the k square, and we know that k is very much greater than 1. Then we can go to the basic equation for the pressure P by P infinity here. So PE by P infinity, let us write this equation P by P infinity, PE by P infinity, that is equal to 1 plus A1 into chi bar, where A1 is a constant. So the pressure equation is 1 plus A1 into chi bar. So this equation demonstrates for like the strong interaction region, right? So what are the inference from these particular equations? Say first one, let us say the PE by P infinity depends only on chi bar, right? And hence chi bar is the governing similarity parameter for induced pressure change. So chi bar is a governing similarity parameter, for induced pressure change. again, the second point, we can say that the induced pressure change is varying linearly with the chi bar, right? So we can write induced pressure change varies with chi bar, right? So we will have just an overview. Initially, what we have considered is d del star by dx is larger, right? D del star by dx is larger, and then we consider k square is greater than 1. Then we know the basic PE by P infinity equation, that 1 plus gamma into gamma plus 1 by 4 k square plus gamma k square into root of gamma plus 1 by 4 square plus 1 by k square. So by considering k square tends to a larger value when compared to 1, we can simplify this equation. And we already know k is m infinity tau or m infinity theta and m infinity into d del star by dx. Then we have equation del star. Now we want to couple the equation, boundary layer equation with the outer inviscid layer, right? So we write the equation del star, and from the del star, we calculate del star, right here del star. Then from that we calculate d del star by dx, right? D del star by dx, and d del star by dx is proportional to c into mu infinity by rho infinity v infinity power 1 by 4 into m infinity power 1 by 2 x power minus 1 by 4, right? So we have the PE by P infinity equation again, right? So d del star by dx, right? So k square is finally equated to chi bar, and PE by P infinity, while substituting in the basic equation by neglecting the k 1 by k square, that gives P by P infinity is equal to 1 plus A1 into chi bar. A1 is a constant, and this equation demonstrates that P by P infinity is like it depends on chi bar, and the chi bar is a governing similarity parameter for induced pressure change. And the second point is induced pressure change varies with chi bar. So these are the characteristics of the strong shock interaction, strong viscous interaction, right? And we will look into the weak viscous interaction in the next class, again by considering this k square is very much less than 1, right? So k, which is equated to theta, which is equated to tau, that you remember, right? Anyway, so these are the inference from the strong viscous interaction. I stop at this point. Thank you very much.